Well, hello once again, everybody. We're going to go right on to the second half of Chapter 3. This is going to be pages 104 to 117 in the textbook, and just a heads up, I fully anticipate this being a relatively short video. That's going to happen from time to time, especially for the second video um, of our week, and I think that's going to be the case here. So what are we going to talk about today? Well, we'll talk about activated carriers, really. That's going to be the focus of this entire lecture. We'll start with ATP as a specific example of an activated carrier. It is, as it says on the screen, the ultimate activated carrier. We'll talk about how ATP is used to combat the loss of entropy in ligation reactions, where we're making polymers. And then we'll move on to the second most common activated carrier, ones that we'll be talking about quite a bit in just a couple of weeks, electron carriers, specifically NAD plus and FAD. We'll close out with some other activated carriers that are used less commonly, and then we'll tie it all back together to things we've learned already, such as making polymers. So before we go into the details, what really do we mean by an activated carrier? We've talked quite a bit about spontaneous reactions and the need to bribe the universe with released free energy. That free energy can either be in the form of heat or a gain of entropy, but we have to bribe the universe if we want reactions to occur. Non-spontaneous reactions with a positive delta G simply won't occur, and so we have to get that delta G negative for these reactions to be possible. But on the same token, when we do an exergonic reaction and we have a negative delta G, especially if that negative delta G is very high, highly negative, we don't have to give the universe all that energy, right? We're talking about a bribe. We can keep some of that energy for ourselves and use it for cellular processes. The universe wants a piece of the action, but we don't have to give the universe the entire profit of that energy. And so it becomes this kind of balance between releasing enough of that energy as free energy from a reaction that the reaction will actually proceed, but reserving as much of that energy as we possibly can to power our own cellular processes. And I keep using this term energy, right? Energy, but energy is just that. It's not a substance, it's not matter. Energy is largely intangible, it's ethereal, it's hard for us to wrap our mind around. And so what we see in living cells is that that energy, that free energy, is captured and carried by activated carriers. Activated carriers are small organic molecules that have high energy bonds created with this energy. And so the potential energy released as a negative delta G is recaptured as the potential energy in bonds of these activated carriers. So the energy is moving as a bond, as a rubber band, a stretched out rubber band that contains energy of want, potential energy. Holding that released energy in the potential energy of those bonds is how we move this energy around. And these activated carrier molecules can easily move around the cell. They can diffuse through the cell. They can even move around the body and the circulatory system. And they can bring that potential energy to wherever it's needed. And then those bonds can be broken and that potential energy can be released as a negative delta G and be used to power other cellular processes. So your textbook has this really nice figure. I'll admit the first time I saw this figure, I was even questioning even putting it in the lecture, but I like this figure. I think it does a really good job of summarizing a lot of the concepts we've talked about already and bringing them into the context of what we're talking about here. So let's start on the left-hand side here. Here we have a catabolic process. We're going to be breaking food down and extracting energy from it. But that's an oxidative process. It's oxidative because oxidative reactions are spontaneous. They have negative delta Gs. We've learned that already. It's an oxidizing reaction because we're breaking bonds and stealing the electrons of the bonds. It's in those bonds and in the electrons of those bonds where the energy lies. We've talked about that before. And then we capture that energy. When we release that energy, we can put it onto an activated carrier. We can load an activated carrier with that energy. What's not shown here is that what we're actually doing is we're creating a new or a small number of new covalent bonds in this activated carrier. And this energy is trapped as the potential energy of those bonds. Now this activated carrier, this carrier that has that potential energy as part of it, can bring that energy to other parts of the cell or the body for anabolic processes, building processes. Now, anabolic processes begin with small monomers or small molecules in the cell, and then they use those small monomers to build new, often polymers in the cell. And when we do this, we go from monomers to polymers, we're decreasing entropy, we're increasing order, making those reactions energetically unfavorable. They have positive delta Gs. But if in order to do that reaction, we're releasing the potential energy of the carrier, we can offset this positive delta G with the negative delta G of this energy release, and we can bribe the universe with the difference. Now, when we do that, we're going to release all of that potential energy from the carrier, and the carrier will become inactive, it's energy poor, but that carrier can then go back to where it started and pick up new energy from a catabolic process and deliver that energy as covalent bonds to an anabolic process and combat that loss of entropy with energy release and then go back and pick up more energy, and it becomes this cycle. So essentially what we're doing here is we're coupling the release of potential energy that we got from food with the loss of entropy of building the molecules that we need. And it's the activated carrier that's joining those two, coupling those two, and offsetting the positive delta G of our anabolic processes. So as we'll see in week 6, when we talk all about aerobic respiration in detail, that's glycolysis, the citric acid cycle, the electron transport chain, etc. And in fact, even though we won't go into many other catabolic pathways, it's true for many other catabolic pathways, most of the energy that is released in any catabolic process is released from breaking the covalent bonds of things we've consumed. Those covalent bonds contain potential energy. I can't say it enough. Those covalent bonds are like stretched rubber bands. They have energy of want. And when you break those bonds, it's like breaking the rubber band. And when you break a rubber band, potential energy becomes kinetic. And when you break the bonds, you can capture the energy released by those bonds. The fact of the matter is, when that happens, when we do catabolic processes and we break bonds to break food down, most of the energy that's released is captured. It's actually a very small amount of the energy that's released as actual heat, as actual free energy. And that, again, is the universe's bribe. We can't capture all the energy because then the reaction would have a delta G of 0, and it would be at equilibrium. And remember, cells are striving to stay in disequilibrium. So we have to release a little bit of that free energy as heat in order to bribe the universe, but most of that negative delta G is captured as an activated carrier. And it's captured more specifically in a coupled reaction. We talked about coupled reactions before in this class. As a reminder, that's when we have a reaction with a negative delta G, such as breaking a covalent bond, linked to a reaction with a positive delta G, such as making a new high energy bond of an activated carrier. That's how it connects. And these reactions are linked or coupled by a shared product and reactant relationship. So another great diagram from the textbook. Here they have all the way on the left a rock falling. It looks like a rock to me. And as that rock is falling, that's kinetic energy. And when that rock impacts the ground and breaks into little pieces, much of that energy is converted into heat. So that has a negative delta G. However, what we can do is we can put some kind of turbine here so that as the rock falls with all of that kinetic energy, it causes this turbine to spin. A lot of that kinetic energy is converted into energy of motion. And then when the rock hits the ground, it is going to hit the ground, but it's going to hit the ground with less speed because it lost a lot of its falling energy to this turbine. And so it's going to release less heat. See how long the heat arrows are here, representing a lot of heat release, and how short they are here. The heat is much, much less. And the balance of that, the rest of the energy that wasn't released of heat, was the energy used to lift this bucket, to do work. And that work is useful. It's giving some good to the system. So if we think of this thermodynamically, again, this has a very high negative delta G because it's releasing all of its energy as heat. The lifting of the bucket, of course, has a positive delta G because it's losing entropy, it's doing work. But the negative delta G is bigger than the positive delta G. I intentionally made this font bigger than this font because the difference between this, let's say this is 10 units, negative 10 units, this might be positive 8 units of free energy. And the difference between that, negative 2 units, is what the universe is getting as the bribe. That's the heat that's released and increasing the entropy of the local system. And the shared product reactant in this example is the turbine. It's the thing that's allowing the product of one reaction, the falling rock, be one of the starting things, the reactant of the second reaction, lifting the bucket. And for our purposes today, The unfavorable reaction that has the positive delta G that we need to drive forward is the creation of a high energy bond linking something to the activated carrier. The activated carrier will contain more potential energy than it did before because a high energy bond was created. But if that's a high energy bond, that means a lot of energy had to go into making that bond. That reaction had a positive delta G, so we need something else with an even higher negative delta G to offset it. It's all going to come down to making these high energy bonds, stretched out rubber bands that contain a lot of potential energy. And that brings us to ATP, adenosine triphosphate, which is hands down and by far the most widely used activated carrier in biological systems. Adenosine triphosphate is exactly that. It's an adenosine nitrogenous base linked to a ribose sugar, and on that ribose sugar are also three phosphates, triphosphate. And ATP is nothing more than an activated carrier. Those high potential energy bonds that we've already talked about, right? Taking three negative phosphates and jamming them together in close proximity, creating a huge amount of energy of want. All those same negative charges want desperately to repel from one another and get away from another, but they can't because of the covalent bonds linking them close together. All that energy, that potential energy of want, that potential energy of repulsion, is being made by reactions that have a very high positive delta G. In order to take that third phosphate and jam it on to an adenosine diphosphate that already has two, you have to force that third phosphate on. You have to put a lot of energy into that reaction to link that third phosphate on. It is that energy that you put into the reaction that is trapped in that bond. That's the potential energy that that bond contains, but that reaction has a very, very high positive delta G. The reaction doesn't want to happen. In order to make that possible, we must couple that reaction, the adding of the third phosphate, to an even more spontaneous oxidative reaction with a very high negative delta G. We have to have this happen. In this example, the lifting of the bucket is the adding of the third phosphate onto ADP. Doesn't want to happen, requires a lot of energy. So we need another reaction coupled to it that releases even more energy than the energy we need to make ATP. That's what we're getting at. However, once ATP is made, it's a very small molecule, it's diffusible, it easily moves around the cell, easily moves around the body, and as it moves, it's carrying all of that potential energy of that repulsive bond, of that third phosphate bond, wherever it goes. And then that bond can be broken, and when that bond is broken, all of that potential energy is now released as free energy. We recapture that negative delta G. And we can then use that coupled with other non-spontaneous reactions and drive those positive delta G reactions forward. So if we start up here with ATP, adenosine, triphosphate, 1, 2, 3 phosphates, all negatively charged, all held together by these high energy bonds, these bonds that are combating the repulsive energy of want of these negative charges trying to repel. We can we can make this bond starting with adenosine diphosphate and a single phosphate group. We can make this third bond and add this third phosphate by adding energy into the system. Energy has to go into that reaction because that reaction has a positive delta G. That energy can come from the breakdown of food if we're an heterotroph. That energy can come from photosynthesis and sunlight if we're an autotroph. But we got to put energy in. We got to use work to add this third phosphate to where it doesn't want to go. Once we make ATP, we can hydrolyze that bond, and now energy comes out. All the potential energy that was stored in that bond is released as free energy, and that free energy can drive things forward. That's a negative delta G. But that leaves us with a much lower energy adenosine diphosphate. So to recycle the system and take a third phosphate and cram it on, we're going to have to put effort in, we've got to put work in, and that's going to take energy from either catabolic processes or photosynthesis. So in this way, what we're really doing is we're pushing the energy of our food down the assembly line, if you want to think of it that way. We consume food, and the bonds of those food molecules contain potential energy. We break those food molecule bonds down and release that potential energy and trap it into the covalent bonds of ATP. ATP is more universal. It's accepted by more cells. So ATP can then diffuse throughout the entire body and deliver that food energy in the high potential energy bond of its third phosphate. Then ATP itself can be broken down, releasing that potential energy yet again to drive other cellular processes forward. And then most of the molecules are ADP. We need to make ATP with those molecules by using more food that we've just consumed and digested. And we have this cycle of ATP shuttling energy from the food to our cellular processes. ATP is the activated carrier. ATP is picking up energy through aerobic respiration and delivering that energy to the parts of the body that need it. And it's this beautiful cycle of energy moving from where we get it to where it has to go. And ATP is the carrier. So we keep referring to this coupling, but how is this coupling really achieved? How do we actually drive reactions forward with ATP? And the short answer is the coupling is achieved by transferring the actual phosphate that's released when we break that third phosphate bond. So as we hydrolyze ATP into ADP and a phosphate, we take that third phosphate and we transfer it to something else. The product of the hydrolysis, which is the third phosphate, becomes a reactant in the subsequent reaction. So by transferring the phosphate from ATP to another molecule, we are quite literally transferring the potential energy with it. And we call these kinds of reactions phosphorylation reactions. Because the next thing, here we see two carbons of the next target, the next thing is being phosphorylated. It's gaining a phosphate group. But since it's gaining a phosphate group, it's gaining a negative charge, it's gaining potential energy. We're going to see reactions like this again and again and again this semester. Phosphorylation reactions are probably going to be the most common reaction type that we discuss. They're super common, very widely used, and so we want to get comfortable with the fundamental parts of this concept because we're going to see this specifically applied very often in this course. Again, ATP is the universal energy molecule of life. It is often thought of as the energy currency. Not to be too xenophobic, but the US dollar really is a global currency. There are other countries that have adopted the US dollar as their currency, but you can use the US dollar in most other countries. The US dollar is more widely accepted as a national currency than anywhere else, meaning you can use it to buy things anywhere you go. ATP is that same idea for energy in the body, right? When we consume sugars, that energy is only useful to certain cells with certain enzymes. When you consume fats, that energy is only useful to certain cells with certain enzymes. We can extract energy from proteins, not much, but we can do it. But that requires its own set of energies. For each of these macromolecules, when it's consumed and digested, you need a specific set of enzymes to access and trap and use that energy. Not so for ATP. Every single cell can use ATP for energy. ATP is the US dollar of the cell. It is the form of energy that any cell can use. And so when we make ATP, we're putting that energy to the best and most widest use. ATP is used by some cells to power pumps for active transport. It is used in other cells for motor proteins to either do muscle contractions or to move things around a cell. All of the anabolic biosynthesis pathways are using ATP in ways that we'll discuss in this lecture. Enzyme regulation requires an ATP and so many more examples. So when we take the energy from the covalent bonds that we consume and we put that potential energy into ATP, we're putting it into a form that can be widely used by many, many cells for many, many reasons. All right, so what is ATP actually doing, right? It's an activated carrier. Great. It has potential energy in that third phosphate bond. Makes sense to me. I've got it. But how are we tapping into that energy to make things happen in the cell? So let's take this very generic ligation reaction or a joining reaction as an example, and we'll make this a condensation reaction, something we're already familiar with. We have monomer A and we have monomer B. These could be two amino acids, two sugars, two nucleotides. And we want to link them together. We want to polymerize them. We want to make the molecule AB. And because it's a condensation reaction, we're going to lose water. We're going to lose a hydroxyl group from one of these molecules, a proton from the other, and we're going to make water. So nothing new. We've seen this before. In this reaction, A was joined to B. In the polymerization reaction, water was released because it was a condensation reaction, and entropy went down because we went from two different molecules to a specific sequence of one. So we've lost chaos, we've lost entropy. And since we've lost entropy, this reaction should have a positive delta G. It will be non-spontaneous. But this reaction can be driven forward despite that positive delta G if we couple this reaction with ATP hydrolysis. If we couple this reaction with ATP hydrolysis and the amount of energy we release by breaking that ATP is greater than the amount of energy we lose by doing this polymerization reaction, we can bribe the universe with the balance. So to do that, first, the molecule A is going to be activated. AOH is going to actually become phosphorylated AO. And where did that phosphate come from? It came from ATP. So here's step one. Here's our A with a hydroxyl group. And we're going to hydrolyze an ATP and release a lot of energy from the breaking of that third phosphate bond. A big negative delta G here. But we're going to take that third phosphate and physically attach it to A. That reaction has a positive delta G, but it will happen because the positive delta G of phosphorylating A is less than the negative delta G of breaking ATP. So we've got a little bit of extra negative delta G that we can give to the universe as heat. So this reaction occurs. But there's a lot of potential energy in this bond that links the phosphate to A. So this is now activated. We bring B in. Well, B links up with A, giving us our product, but to create that product, we had to release the phosphate group. Well, when we broke the bond to release the phosphate group, we released a lot of that potential energy, once again bribing the universe with heat. So yes, entropy went down here. This had a positive delta G, but that was offset by the breaking of this bond, releasing heat as an even higher negative delta G. And the universe was bribed twice in a row. The amount of energy in the ATP was great enough and sufficient enough that we could bribe the universe once with that energy to add the phosphate to A, and then a second time with a negative delta G to add B to A, giving us what we wanted, which is AB, and giving the universe what it needed, which was energy release and a negative delta G. And so this is how we couple the breakdown of an activated carrier to some entropy losing reaction. And we drive reactions that have positive delta G's forward by coupling them to reactions with an even greater negative delta G. So again, as stated in the last slide, the actual phosphate is transferred from ATP, where it's really high energy, to A, where it's slightly less high energy. So still a lot of potential energy in the phosphorylated form of A. And then when we break the phosphate off of A, we release energy yet again, and that energy offsets the loss of entropy of joining A and B, making the overall reaction have a negative delta G and be spontaneous. So that's a generic example, right, with this A and B. Let's look at a real example. Let's turn glutamic acid, which has a hydroxyl group on its side chain, to glutamine, which has an amino group, a nitrogen group here on its side chain. So that's decreasing entropy, increasing order. We want to turn this into this. That's going to have a positive delta G. It's not going to happen. So it's non-spontaneous. However, we can pull a fast one. Let's do this. Let's get ATP involved. And let's do phase one, the activation step. Let's hydrolyze ATP into ADP and release a lot of negative delta G, a lot of free energy. Let's give some of that free energy to the universe so that this reaction will occur, but let's use the balance of that free energy to take that third phosphate that we just released and put it onto what was glutamic acid. Essentially replace the proton with a phosphate group. Now again, this phosphorylation has a positive delta G, but its positive delta G is less in number than the negative delta G of ATP hydrolysis. So the universe just won. And there's a lot of potential energy in this bond right here. So now step two, let's offer the amino group. Here it's ammonia because it's free. Let's offer ammonia to this activated molecule. The ammonia is going to break this high energy bond, releasing that energy as a large negative delta G. And yes, we've decreased entropy by adding ammonia, now an amino group, but that reduction in entropy is less than the energy released by this hydrolysis of the phosphate. So the universe is bribed in step one, and the universe is bribed in step two. Both of these steps have a negative delta G. Granted, a very small negative delta G. The universe isn't getting that much energy, but it's a negative delta G, and so the reaction will occur. So that's how ATP is used for these phosphorylation events. That's how ATP is used as an activated carrier. Let's turn our attention now to electrons and the activated carriers that carry them. It's not just ATP and phosphates that can pull off this kind of switcheroo on the universe, this double bribe to get what we really want. Electrons can also be used the way that phosphates were just used. Electrons are what covalent bonds are made out of. And so electrons carry a lot of potential energy in them. They literally carry the potential energy of the covalent bond because it was the electrons that made the covalent bond. And so by moving and carrying electrons around the cell, we can move and carry energy, just like we did with the high energy phosphate bonds we talked about a moment ago. Carrying and transferring high potential energy electrons by using those electrons to make new high energy bonds allows us to move energy around the cell just as efficiently as ATP does. And our carriers of that energy, the carriers of the electrons, are molecules such as NAD and NADP, and also FAD. When those carriers have been reduced and they are physically carrying electrons, they are capable of making new bonds because they've gained electrons, and they typically make those bonds with the most plentiful atom around, which is hydrogen. So reduced NAD becomes NADH, reduced NADP becomes NADPH. That's when they're carrying their electrons. We can see that here. Here's molecule A. Molecule A is covalently bound to a proton, and there's potential energy in this bond. But let us not forget what this bond is. It's a pair of shared electrons that is orbiting between A, or an atom in A, and the hydrogen. Oops. And so that potential energy, that stretched out rubber band of that covalent bond, has energy to offer. We're going to oxidize A. Remember, oxidation is the theft of electrons. So we're going to break this bond and release its potential energy, and we're going to steal an electron of that bond, thereby stealing that potential energy. A becomes oxidized. It has had energy and electrons stolen from it. But we can't just have electrons around. They're too radical. They're too wild. We have to put them somewhere. So we immediately take the electrons that we stole and we put them on an electron carrier, such as NADP. We give the electron to NADP, but since we've given NADP an electron, we've given it the opportunity to make a new covalent bond. It makes a new covalent bond with hydrogen, and NADP has now become reduced. It is now NADPH, reduced form. And it contains a new bond, and that new bond contains potential energy, the potential energy that is being carried by the electrons making that bond. Now, NADP can go elsewhere in the cell or elsewhere in the body, and it can give up its electrons. NADP can be oxidized, and it gives up its electrons to something else like B, reducing B and giving B that energy. Now that energy lies here in the potential energy of this bond with B. And so we've transferred energy from the potential energy of a bond in A to the potential energy of a bond in B, but the way we've moved that energy is by moving the electrons. And NADP was the activated carrier that carried those electrons from A to B. And it's worth pointing out that this was a redox reaction. Things were reduced and gained electrons, and things were oxidized and lost them. And in fact, it was two redox reactions. A being oxidized while NADP was reduced, and NADPH becoming oxidized as B was reduced. So these activated carriers of electrons, they carry 2 electrons each, and because when you give something an electron, you've given it the opportunity to make a new covalent bond, and because hydrogen is so plentiful in the cell, typically with these redox reactions, where the electrons go, the hydrogens will follow. And so if we see something gain a hydrogen in the context of a redox reaction, we know that that was the molecule that was reduced. So here's NADPH in a little bit more detail. We see its ball and stick model here on the left. We see the entire molecule here as well, and we can see its reduced and its oxidized forms. So you can see here that it's very nucleotide-ish. It's actually 2 riboses and 2 nitrogenous bases that are held together covalently. And it's here on the nicotinamide ring where we have the actual oxidation reduction. This is the reduced form. I know that because we've got an extra electron and we've got an extra proton. And this is the oxidized form where we see those electrons and that proton is gone. So oxidized, empty, no extra energy, reduced, carrying electrons. And if it's carrying electrons, it's carrying potential energy. It's the activated carrier. I mentioned earlier NAD. NADH and NADPH, again, those are their reduced forms because they have the hydrogens on them. They differ only in the presence or absence of that one phosphate. That's what the P stands for. And that phosphate's really far from the electron carrying site. If we go back to this example here, we can see that that phosphate that differs between the two is on the exact opposite end of the molecule as where the electrons are accepted. So clearly that phosphate plays no role in carrying the actual electrons, and it doesn't. All the phosphate does is change the shape of the carrier, and by changing the shape of the carrier, it changes its function. The different shapes of these two carriers, the different shapes between NAD and NADP, or NADH and NADPH, causes these two different carriers to fit into the active sites of different enzymes. And so this gets us back to the idea of specificity. NADPH carries electrons for anabolic processes. When electrons are needed for making polymers, when electrons are needed for making sugars, as we see in photosynthesis, when electrons are needed for any anabolic process, we invariably see those electrons being carried by NADPH. NAD itself is chiefly involved in catabolic or breaking down processes, such as breaking down sugars and aerobic respiration, breaking down fats in a process called beta oxidation. So whenever we're doing a catabolic process and we're scavenging and harvesting electrons to trap their energy, we're going to see NAD is involved. NADH is its reduced form. So this is just another example of segregating and compartmentalizing. NADP and NAD fit into different enzymes. They can get into different parts of the cell. They both carry electrons, but for completely different roles. NADP carries electrons from making new molecules, and NAD carries the electrons that were harvested from breaking food molecules down. And by having two different carriers that work with two different sets of enzymes, we separate these two processes and we allow for the processes to be independently regulated. So we're going to see ATP a lot. We're going to see NAD a lot. NADP, we are not going to see all that often, but we'll see NAD quite a bit in just a couple weeks. But there are also other carriers that we should at least be aware of, even if we won't encounter them very often. And these other carriers, they don't carry phosphates. That's what ATP is for. They don't carry electrons. That's what the electron carriers are for. They carry other high energy things, things that are important for the cell. And so this is table 3.2 from your textbook, and it shows a lot of the biological carriers. On the left, you see the carrier itself, and on the right, you see the high energy thing that it's carrying. So we see that ATP is the carrier for high energy phosphates. NAD, NADP, FAD are the carriers for high energy electrons. Well, acetyl-CoA, and CoA specifically, is an activated carrier for acetyl groups. Acetyl groups contain energy. It's the energy that we release by the citric acid cycle. So CoA is the carrier, and when that carrier is activated, it's carrying acetyl. Carboxylated biotin is an activated carrier. The high energy group is a carboxyl group. Biotin is the carrier. S-adenosyl methionine is an activated carrier, but it's a methyl group that actually contains the energy. And then we even have carriers for glucose. UDP is the carrier, and glucose is the high energy molecule. UDP glucose is the activated carrier. So there are carriers for all of these things. We'll focus on coenzyme A in just a second, CoA. But again, just important to note that for every high energy molecule that a cell needs to use, there'll be a carrier that can be activated to carry that high energy molecule. And CoA is the carrier for acetyl groups. It's the acetyl carrier. So here's acetyl-CoA in all of its glory. You might not have ever seen acetyl-CoA before, but this is it. This is all CoA right here. We have a ribose sugar. We have a phosphate coming off of that ribose sugar on its 3' carbon. We have an adenosine here, a nitrogenous base, adenine. We've got two phosphates coming off of the 5' carbon, And we got a whole bunch of hydrocarbons, a carboxyl group. We've got even a nitrogen group here, then a sulfur, and then here is the acetyl, the little two carbons, two carbon acetyl. So you've got this huge molecule, huge in size and in atom number, all to carry a very small, though high energy, acetyl group. So acetyl-CoA exists as an activated carrier of acetyl, a two-carbon molecule, two-carbon functional group. And you may remember from Bio 107, if you've had me especially, we harped on this, or maybe from other courses, it's acetyl-CoA that we make from pyruvate. At the end of glycolysis, one glucose is converted into two pyruvates, and then pyruvate is processed into acetyl. Acetyl is linked to CoA, as we see it here, and then CoA delivers acetyl to the citric acid cycle. And the citric acid cycle gets to work breaking that acetyl down and robbing as many high-energy electrons as it possibly can. Most of this CoA molecule, as you can see right here, is not for carrying acetyl. So why is this molecule so big and complex? It's this big and complex for the same reason that there's a phosphate on NADP and not a phosphate at NAD. This molecule is so big so that there's specificity for the right enzymes. The complexity of coenzyme A gives an enzyme a great many non-covalent bonds it can make with CoA and recognize it with a high degree of specificity, so that only CoA is going into the active sites that should receive it, and only acetyl is being delivered to those enzymes. Also, interestingly, as I've already pointed out, much of CoA is an adenine ribonucleotide. Basically looks almost like an A of RNA. Why is that? We're not really sure, but it gets back to this idea of an RNA world hypothesis. There's a lot of evidence, this being some of it, that the very first biomolecule, the first molecule that was catalytic and capable of transferring information and seeing to its own reproduction was RNA. Many of us believe, myself included, that RNA was the first true functional organic molecule on this planet. And we see vestiges of that. We almost see conceptual fossils of that all through life even today. So CoA, being such an important molecule, is probably built on an RNA backbone because RNA was the most plentiful and most successful molecule on prehistoric Earth. All right. So getting back to making polymers, making macromolecules requires energy. We're decreasing entropy, and the only way we can combat that decrease of entropy is by releasing free energy, releasing enthalpy, and getting that delta G negative. We've hit on this a lot. Macromolecules are made by joining monomers together into a polymer, almost always by a condensation reaction. Water is released, and in doing so, you're going to decrease entropy, and that reaction is going to be non-spontaneous. And that's the reaction we see here. Right? We've got the OH from A and the proton from B, and we're going to join A and B together and release the water. Doesn't look favorable to me. I don't see any benefit to the universe here. The universe just lost chaos. Now, I get the hydrolysis of the bond between A and B would be favorable because ordered AB is becoming less ordered, more entropic A and B separate. So I understand why the hydrolysis reaction has a negative delta G, but how did we get away with the condensation reaction? Well, we kind of know the answer to that already, right? We've touched on an example of that. What we haven't covered yet is that whether it's the addition of a sugar, such as we see here we're adding a glucose to a growing chain of glycogen. Glycogen is a polysaccharide, it's a polymer. We're going to do a condensation reaction, as you see on the screen, to add one more glucose monomer to the chain, and in doing so, we're reducing entropy. Or whether it's the addition of a nucleotide. Here we have an adenine and a cytosine linked together in a chain of RNA. Here comes guanine as a free nucleotide, and we're going to do a condensation reaction, pull water off, and link that guanine onto the growing chain, and entropy just went down. That has a positive delta G. Or whether it's even the addition of an amino acid. This is the condensation reaction we hit so hard in a previous video and in class. We're removing water, essentially water, from two different amino acids, and we're joining those unpaired electrons together to make a peptide bond. Water is released, and entropy goes down, this reaction has a positive delta G. Doesn't matter if we're adding a sugar to a growing chain of glycogen, a nucleotide to a growing chain of RNA, or an amino acid to a growing chain of peptide, we have a positive delta G. And if we want that reaction to occur, despite that positive delta G, we have to bribe the universe. We have to make that reaction spontaneous. We have to make that reaction have a negative delta G. And we're going to do that by coupling these reactions with the hydrolysis of a triphosphate. If that's the case, where are those phosphates coming from? They're coming from the activated carrier for them, ATP. So ATP is hydrolyzed, an enormous amount of energy is released. Some of that energy is used to jam that third phosphate onto the monomer, and the rest of the energy released is bribing the universe, keeping that first phase or that first step spontaneous, negative delta G. But still, there's a lot of potential energy in the bond between the phosphate and A. In comes B. B, by breaking that high energy bond, gets joined to A. We win. We got the polymer to form. But when B breaks that high energy bond between A and the phosphate, that energy is released as a negative delta G, and the universe wins too. And everybody is happy. Entropy went down, yes, but a lot of energy was released to do it. That energy released as heat made the molecules around the system move more chaotically. The universe is fine, and life can persist because we made our polymer. So let's tie up some loose ends here. Maybe it's not surprising. It's more complicated than that for many macromolecule synthesis pathways. A lot of times we have to do multiple steps of activation, such as this. So many times we have to cleave two phosphates off of the triphosphate individually. So we release energy here as we get rid of this high energy bond, and then we release high energy a second time. We often have to do this in order to make polysaccharides or polynucleotides. We have to get a double bang for the buck out of that. That becomes very complicated biosynthetic pathways because they're multi-step, multi-releases of the phosphates, multi-activation steps. So it gets more complicated. And also, to be clear, phosphates and electrons aren't limitless. They're not magic. They can't make anything happen. The hydrolysis of ATP to ADP has a delta G of roughly negative 50 kilojoules per mole. That is a lot of energy, trust me, but of course it's not a limitless amount of energy. So we can only drive a non-spontaneous reaction forward with an ATP hydrolysis if that non-spontaneous reaction has a delta G of positive 40 kilojoules per mole or less. We have to have at least roughly 10 kilojoules per mole difference between the two in order to bribe the universe. So what happens if we have reactions that require more than 40 kilojoules per mole? Well, that's when we have to do these kinds of things and release the 50 kilojoules per mole on the first cleavage and another round of kilojoule per mole release in order to continue to make the universe happy as we have these very, very low entropy reactions occur. But these kinds of reactions are too complex for the scope of this class. You might get into some of these kinds of reactions in biochemistry, you might not. If you go into graduate school in biology, you'll definitely talk about some of these, but we don't have to go into it that closely. What I really want you getting out of this material here is the importance of energy transfer, how important it is to have spontaneity in our reactions, and how the cells achieve that spontaneity in all the many ways that they have to. So as we close out this chapter, chapter 3, and we are going to leapfrog 10 chapters ahead, we're going to go straight into chapter 13, which is the chapter on metabolism. I want you to keep those fundamental principles that we've learned so far in mind. Those ideas of Gibbs free energy, the idea of bribing the universe. We have to have some kind of negative delta G at the end of what we're doing so the universe has what it needs. That coupling reactions is a primary strategy for doing that. And now what we've introduced here, this notion of energy carriers, ATP being a carrier for high energy phosphates, NAD, FAD, and NADP being an electron carrier for high energy electrons. We have these dedicated molecules whose sole job it is to absorb potential energy on one side of a reaction, and that's usually a catabolic side, and deliver that energy to a reaction that has a positive delta G. And by coupling these reactions and bridging these energy transfers, we can keep the universe bribed, we can keep everything at a negative delta G, and we can make life possible. So to summarize, what did we talk about here? Well, metabolism consists of two halves, breaking and making. Whenever we're breaking molecules down to release energy that we trap in carriers, and also to release monomers that we're going to recycle and use for ourselves, that's going to be a catabolic pathway. And then we can use those monomers and the energy that we've captured to build the molecules we need. And that's the anabolic side. The anabolism half of metabolism is the making side. So we have breaking, catabolism, and making, anabolism. Energy is stored and transferred in cells using activated carriers. Carriers for phosphates that contain a lot of potential energy. That would be ATP as the carrier. Carriers for electrons that contain a lot of potential energy. Those carriers are NADH and NADPH as examples. And FADH2. Can't leave FADH2 out. We're going to be seeing that in a couple weeks. Activated carriers, whether they're carrying phosphates or they're carrying electrons, are carrying energy. And they're carrying that energy in high energy, high potential energy bonds, covalent bonds. That's either the bonds between negatively charged phosphates that have a lot of repulsive energy of want, or the electrons themselves are making the bonds, thereby carrying the energy directly. And it's this energy in these high energy bonds that can be released as kinetic energy and drive biochemical reactions forward that would otherwise have a positive delta G. ATP is the universal energy molecule of life, and it allows systems to be coupled. It couples energy release through the hydrolysis of ATP with energy requiring processes that are largely anabolic. Phosphorylation reactions directly transfer the energy of that third phosphate bond to other molecules by phosphorylating them. And this enables a diverse amount of cellular activities. The one we really drilled down here were polymerization reactions, dehydration reactions. Turning to electrons, NADH and NADPH both have distinct roles. NADH is catabolic. It collects electrons that are released by the breakdown of food, and NADPH is anabolic. It delivers those electrons to anabolic pathways that are making polymers for the cell. Macromolecule synthesis is those polymerization reactions that we're talking about, the condensation reactions that make polymers, and this reduces entropy. When you're making a polymer, entropy goes down. And so those positive delta G reactions ain't going to happen unless you couple them to an energy releasing reaction. And that's the energy input being referred to here. Most of the time, we see that ATP is doing the coupling. We're coupling the hydrolysis of ATP with the entropy reducing synthesis reaction, and we can drive those reactions forward, achieving an overall negative delta G of the two reactions combined. So coupled reactions combine favorable reactions with very high negative delta Gs with the unfavorable non-spontaneous reactions that have slightly lower positive delta Gs, so that the overall sum delta G of both reactions occurring together is moderately negative, and that allows the reactions to occur. Moving beyond electrons and phosphates, acetyl-CoA is an activated carrier of acetyl groups. CoA is the carrier. This is also essential in catabolic pathways such as the citric acid cycle, which we'll be seeing soon. Free energy, or delta G, change in free energy, is really what we're looking at to determine whether or not a reaction is spontaneous, and cells maintain disequilibrium. We cannot have a delta G of 0. We must keep those delta Gs negative to keep these reactions moving forward. And finally, the synthesis of biomolecules and the conversion of energy as we break molecules down and make them both must be tightly regulated to make sure that the cell is functioning properly. So what are we at? Just about 50 minutes, so good. We had 10 minutes, 15 minutes shorter than usual. And yeah, that wraps up chapter 3. If you have any questions, let me know in the box that pops up right now, and we'll cover them in class next time we meet, and we'll keep trucking along. As always, thank you so much for watching, and I'll see you all quite soon in class.